We're going to now proceed with more tests for convergence of a series. And the first test, which I'm going to formulate as usual as a theorem, is going to be a comparison test. All right, how do we state that? So suppose an is greater or equal than 0 for all n, then we have the following. Number one, if the series of bn's, actually if a series of an's converges, and we have that bn in absolute value is less or equal than n for all n, then from this we will conclude that the series of bn's converges. That is the first statement. And the second statement, if, again, the series of an's diverges, right, that is series from 0 to infinity of an is equal to infinity, then and bn is greater or equal than an for all n, so then the series of bn's also diverges. All right, so to prove this, actually, let's prove number one first. Let's see, what do I have? I have that the sum from 0 to infinity of an, this is sum of the infinite series of an's, converges, so this is a finite number, so the sum is a finite number. Then this means, what does it mean that the series converges? It means that the sequence of partial sums converges to a finite number. And we also showed that this means that the sum of that the partial sums form a Cauchy sequence, which I can equivalently state as that the series is going to satisfy the Cauchy criteria. So if the series converges if and only if it satisfies the Cauchy criterion, again, this means, this is simply a different way of saying that the sequence of partial sums is a Cauchy sequence. And now what is a Cauchy criterion? For any epsilon greater than 0, there exists capital N in R such that absolute value of the sum n from L to M of an, that this is going to be less than epsilon as long as L and M are going to be bigger than capital N, right? That's a definition of Cauchy criterion. Okay, so if that is the case, then let's fix M and L. And I want to look at what happens to the absolute value of the sum when n goes from L to M of Bn. Because if I can show that this is less than epsilon, then a series of Bn's also satisfies the Cauchy criterion, and then it converges. Well, what is this? So that's the same thing as BL plus BL plus 1 plus etc. plus the last term in my sum is Bm. And then I can apply the triangle inequality. So this should be less or equal by the triangle inequality than the sum of BL plus BL plus 1 plus etc. So sum of absolute values of the same B's. But then what do I know? I also know that for each index, Bn is less or equal than An, right? By my assumptions. So this is true for all n. And so therefore, the sum of absolute values of B's is going to be less or equal than the sum of just not absolute values, but sum of A's, because A's are positive, rather non-negative. So AL plus etc. plus AM, right? And that is a sum n from L to M of AL, right? But then all A's are positive. So the sum actually is exactly the same thing. So all AN, actually this is not AL but AN. AN are greater or equal than 0 for all n. So this is the same thing as the absolute value of the sum n from L to M of AN. Right, and we know that that is less than epsilon if M and L are bigger than capital N, because a series of A's converges and satisfies the Cauchy criterion. So this then is less than epsilon if M is greater or equal than L, bigger than capital N. And so the conclusion from this, the series of Bn's satisfies the Cauchy criterion, and that is enough to conclude that the series of Bn's converges. Okay, so that proves the first part of the theorem. So now the second part states that if the smaller series diverges, then a larger series also has to diverge. Right? This is kind of obvious. Let's try to write the proof of that. So suppose that the sum n from 0 to infinity of n is equal to infinity. Well, what does it mean? It means that the limit as k goes to infinity of sum n from 0 to k of n, right? So the limit of partial sums must be equal to infinity. Okay, so on the other hand, because Bn is greater or equal than An for all n, right? It follows from this that the sum n from 0 to k of An must be less or equal than the corresponding sum of Bn's, right? Because each individual Bn is larger than a corresponding An. Okay, and if that is true, then what should be the limit when k goes to infinity of the sum n from 0 to infinity of Bn? Well, in this case I have two sequences of partial sums. One is for An, another one for Bn. The limit of a smaller sequence is infinity. So then by comparison theorem for limits, limit of a larger sequence also must be infinity, right? So then this equals infinity by the comparison theorem for limits that we discussed before. Right, and that concludes the proof of the comparison theorem for series. One immediate consequence of this comparison theorem is going to be the following. So, first of all, I'm going to give the following definition. We're going to say that the series of An converges absolutely if the series of absolute values of An converges. And the second definition, the series of Ans converges conditionally if the series itself converges, but the series of absolute values diverges. Notice that the series of absolute values cannot not converge, right? The only possible choice for the series of absolute values, for the series of partial, for a sequence of partial sums of absolute values is to either go to infinity or converge to a finite number, because sequence of partial sums of positive numbers would always be increasing, right? The more positive numbers I add, the larger the partial sum is going to be. And so for monotone sequences of partial sums, these sequences must either converge to infinity or to a finite number. Okay, so with this, let's prove the following result. We have the following theorem. Suppose that series from 0 to infinity of an converges absolutely. And then the series itself, without absolute values, converges. Which means that it is in principle enough to prove that a given series converges absolutely. That will guarantee that the series itself converges. The proof of this is really quick, and it uses a comparison theorem. So what do we have? We have that an, let's see, we have that one second. So we know that the series of converges absolutely. So sum from n from 0 to infinity absolute value of an converges, right? Let's look at the comparison theorem. Comparison theorem, the first item in a comparison theorem states this, that if absolute value of bn is less or equal than an, and the sequence of an converges, then the sequence of, if a series of an's converges, and the series of bn's converges. Well, but in this case, what is my bn? Bn is actually an itself, right? So clearly, absolute value of an is equal to absolute value of n, right? This is a trivial statement. So the series of v's converges, so then immediately, so this is true for all n, and so then immediately from comparison theorem, series of an's must converge. Right, so essentially we already proved this fact. Okay? All right, so we have this. And next, I'm going to prove more convergence tests. And then we're going to apply them for a bunch of examples in the next installment of this lecture. So the next test that I want to demonstrate is going to be a root test that you all know and love. So let's remember the statement. In fact, the statement that I'm going to give will be somewhat different than what you're used to. So this is a root test. Suppose that lim sup as n goes to infinity of absolute value of an to the power 1 over n, suppose that this is equal to some number alpha. So alpha obviously is a non-negative number. So then, number 1, if alpha is less than 1, then a series of an's converges Absolutely. Number two, if alpha is greater than 1, then a series of ANs either diverges or does not converge. And as you might recall from regular calculus, the choice number 3, if alpha is equal to 1, then the test is inconclusive. Okay, let me just give you a little motivation here. And the motivation is really simple. What we're doing, we're saying that absolute value of an to the power 1 over n, lim sup is equal to alpha. So let's assume that limit actually is equal to alpha. So this is approximately alpha, right, if n is big. Well, but if that is the case, then what I actually have is that absolute value of an is approximately alpha to the power n if n is very big. And therefore, if I take a sum of an's, absolute values of an's, this is going to be roughly a sum of alpha to the power n, right? But then what kind of series is sum of alpha to the power n? This is a geometric series. So if alpha is less than 1, then this geometric series would converge. If alpha is bigger than 1, this geometric series would diverge. And so that means that if eventually my series is going to, so this would ensure that eventually my series is kind of going to look like a geometric series. And then if alpha is less than 1, geometric series converges. If alpha is bigger than 1, geometric series diverges, or yes, of positive numbers diverges. And so that is a basis for the root test. Again, if your sequence ants that you're dealing with eventually looks like, or if your series of ants eventually looks like a geometric series, then whether or not the series converges is determined by what the multiplier of that series is going to be. So now let's provide a formal proof of this. And we need to consider 3 different cases. So proof. Our case number 1 is alpha is less than 1, right? So if alpha is less than 1, then there exists an epsilon greater than 0 small enough so that alpha plus epsilon is going to be still less than 1, right? So this essentially is a density of Q kind of result, that if I see alpha and I'll see alpha less than 1 and the number 1, then there must be a number between alpha and 1, which is, of course, still less than 1, and bigger than alpha, and that defines your epsilon. Okay, so then what do we know? We know that lim sup, so because lim sup as n goes to infinity of absolute value of a n to the power 1 over n, because this thing is equal to alpha. If I use epsilon that I just found here, there exists a capital N in R such that, now let's think about it for a moment. What is lim sup of something? Lim sup of something is the limit when k goes to infinity, or the supremum n bigger than k of absolute value of an to the power 1 over n, so equal to alpha. This is exactly the same statement as the one up here, right? So the limit, lim sup, is actually a limit of suprema of your sequence when n is greater or equal than k. But then by definition of a limit, there exists a capital N such that if I take the difference between supremum n greater or equal than k, absolute value of an to the power 1 over n minus alpha, right? And this is going to be less than that epsilon that I chose, right? So once again, because lim sup when n goes to infinity of something is equal to alpha, that means that this actually me taking a supremum of that something when n is greater or equal than k, and then letting k go to infinity. Then by definition of the circled limit for that epsilon, for any epsilon, but in particular for this epsilon that I chose here, there exists a capital N for which the term of my sequence minus alpha must be less than epsilon, right? Again, just the definition of the limit. So I'm going to get rid of this. So this is less than epsilon if k is bigger than capital N. But saying that is equivalent to saying again that minus epsilon is going to be less than sup n greater or equal than k, absolute value of an to the power 1 over n minus alpha, and this is less than epsilon, right? As long as, again, k is bigger than capital N. And then I can add alpha to all three sides, so this would be equivalent to saying alpha minus epsilon is less than the supremum n greater or equal than k, absolute value of an to the power 1 over n, and this is less than alpha plus epsilon if k is bigger than capital N, right? Now, if this is true for any k bigger than capital N, then in particular if I make n bigger than capital N, it will still be true. So therefore, if I set k to be capital N, if I say k to be the first number bigger than capital N, that would be capital N plus 1 actually, supremum n greater or equal than capital N plus 1, absolute value of an to the power 1 over n, that this is less than alpha plus epsilon. Right, so the only thing that I did now is I chose the first k that is bigger than capital N, so I'm replacing k by capital N plus 1, and I'm neglecting the lower bound, right? So this is what we got. But saying that actually is the same thing, and greater or equal than capital M plus 1. This is the same thing as saying supremum n greater than capital N of an to the power 1 over n, that this is less than alpha plus epsilon. And that statement, in turn, is equivalent to saying that absolute value of an to the power 1 over n is less than alpha plus epsilon for any n bigger than capital N. I'm simply using the fact that if a supremum of something is less than a certain number, right, that means that every element in the set, the supremum over which I'm taking, is going to be less than that number, right? Again, alpha plus epsilon, supremum is the least upper bound on a absolute value of an to the power 1 over n. This is less than alpha plus epsilon, so that means that alpha plus epsilon itself is also an upper bound, right? Not the least upper bound, but an upper bound. And so every individual a to the power 1 over n must be less than alpha plus epsilon. All right, but then if that is true, then again, equivalent statement. If I take nth power of both sides, the equivalent statement to that is going to be an absolute value is less than alpha plus epsilon to the power n, again, for any n bigger than capital N. Okay, so then what is alpha plus epsilon? Alpha plus epsilon is a number which is less than 1. What does it mean? It means that now I have a sequence which looks like a geometric sequence, right? Because it's a fixed number alpha plus epsilon, which is less than 1 to the power n. And that geometric sequence is going to be larger than my given sequence, absolute value of an, as long as n is bigger than capital N. So then, if that is true, one additional comment here. So alpha plus epsilon is a positive number which is less than 1. So therefore, the sum n from capital N plus 1 to infinity alpha plus epsilon to the power n, this converges. Right, this is a convergent geometric series. So again, we have two facts. Fact number one is that the series of absolute values of an's is less than the geometric series. And the fact number two, because alpha plus epsilon is less than 1, then if I add up the elements of the series of a geometric series starting from capital N plus 1, then this should be convergent because it's a geometric series with a multiplier which is less than 1. Well, and then what can I conclude from these two statements? That my given series is less than a convergent geometric series. So then by the comparison theorem, what we see is that the sum n starting from capital N plus 1 to infinity of absolute value of an, that this series converges. Why am I starting from capital N plus 1? Because I only have this comparison result starting from beyond capital N. So if I keep adding terms of my series starting from capital N plus 1, by comparison theorem, this addition will give me a finite value. Okay, but then what is the difference between the series starting from 0 of absolute value of an and a series that I know already converges? Well, how can I write a series when I add things starting from 0 all the way to infinity? I can split this into a sum of two sums. One is go from 0 to capital N plus, and then you go from n equal to capital N plus 1, right? That's the next guy after capital N, and this goes to infinity again of n. So what do we know about this guy? This guy converges, right? This is a convergent series. We just proved it. And what do I know about the first term? Well, this is just a sum of finitely many numbers. So this would be a finite sum. So then what is this? That's a finite sum plus sum of the convergent series, which is also a finite number. So the outcome is a finite number. And so the overall series converges, or the entire series converges. So this is kind of an important argument. If I want to prove whether or not a given series converges, it really doesn't matter where I'm going to start adding the terms. I can always ignore, from a point of view of convergence, determining convergence, I can always ignore whatever many terms sit in the front part of my series, because adding those together will just give me a finite number automatically, because it's a sum of finitely many elements. So convergence of a series is determined entirely by what happens in the tail of a series. So if I can show that my series converges starting from a certain index, then that's enough to conclude that the series converges in its entirety if I add all elements of a series. All right, so we proved that the entire series of absolute values of an converges. So that means that the series of an converges absolutely, which I actually, I did state that. Okay, so that proves part number 1. Let's move on to part number 2. So again, here we're assuming that alpha is going to be greater than 1. And let's see what the consequences of that. So suppose that alpha is bigger than 1. That is lim sup n goes to infinity, absolute value of an to the power 1 over n is greater than 1, right? Okay, so then by one of the previous theorems about subsequences, so then we can always find the subsequence which converges to lim sup. So then there exists a subsequence let's say A and K, such that the limit K goes to infinity of A and K to the power 1 over nk, so this is equal to alpha, which is still greater than 1, right? Okay, so then if I have a sequence which converges to a number which is strictly greater than 1, we proved this before in different contexts. If my sequence converges to a number greater than 1, that it means that eventually all terms of my sequence are going to be greater than 1, right? So then starting from some capital K greater than 0, absolute value of a and k to the power 1 over nk, then this quantity must be itself greater than 1. Right, again, I know that this sequence goes to 1, to a number greater than 1, so that means that eventually all terms of my sequence will become greater than 1. Okay, so, and if that is the case, then if I raise both sides to the power nk, then a and k should be greater than 1 to the power nk, which of course is equal to 1 for all k bigger than capital K, right? All right, so is that good or bad? Well, if we assume for a moment that the limit I wish I can write the word limit. Limit as n goes to infinity of absolute value of an is equal to 0, right? Then we know the limit, if the limit of a sequence is something at the limit of any subsequence is equal to that number. So then the limit k goes to infinity of absolute value of a and k must be equal to 0. But that is a contradiction with what we are saying here, right? So this contradicts the fact that a and k is greater than 1 for all k bigger than capital K, right? So again, if the limit of an is equal to 0, then the limit of an k must be equal to 0 for all subsequences, in particular for that subsequence that I chose up here. But for that subsequence, I know that magnitude of a and k is greater than 1 for all k bigger than capital K, so the limit cannot be equal to 0. Which means that this assumption is not true. So therefore, from here, I can conclude that the limit n goes to infinity absolute value of an cannot be equal 0. But that, by the test of convergence, means that the series n from 0 to infinity absolute value of an cannot converge, so it means that this guy should diverge. Right, and if it diverges, then the series itself cannot converge. In fact, if a limit of, let me rewrite this in a slightly different way. If a limit of absolute value of an is not equal to 0, then the limit of an itself cannot be equal to 0, right? So limit n goes to infinity of an is not equal to 0, and so therefore, by the test for divergence, we conclude that the series from 0 to infinity of an, that this guy does not converge. Right, it's either goes to infinity or it oscillates. So that's item number 2, and then item number 3. Let's suppose that lim sup n goes to infinity of absolute value of an is equal to 1. And we need to show that in this case the test actually n to the power 1 over n. In this case, the root test is not going to be conclusive. And to prove that, it will be enough to demonstrate that there exist 2 sequences for which this lim sup is equal to 1, but one sequence converges and one sequence does not converge. So let's look at the example A. Example A. Let's say an is equal to 1 over n. Right, so if an is equal to 1 over n, then if I take 1 over n to the power 1 over n, right, and I want to take a limit of that as n goes to infinity, then we proved before, right, so if I raise n to the power 1 over n, that went to, the limit was equal to 1. So therefore this should be the same thing as a limit n goes to infinity 1 over n to the power 1 over n. That is a limit n goes to infinity of 1 divided by the limit n goes to infinity n to the power 1 over n. And from from before, we know that this is 1 over 1 equal to 1. Okay? And in this case, if I take the series of 1 over n's, this diverges because this is a harmonic series. And in addition to that, one thing that I am missing here, so if a limit of 1 over n to the power 1 over n exists and equal to 1, then furthermore, then lim sup, right? If a limit exists, then lim sup is equal to lim nth, and both are equal to the same thing as a limit. So lim sup is equal to 1. So alpha is equal to 1 in this case, right? So alpha is equal to 1 and the series diverges. Now example number 2. Is going to be something that we're going to discuss pretty soon. So here you just have to accept what I'm saying. So if I use n equal to 1 over n squared, then I repeat the same computation, limit n goes to infinity of 1 over n squared to the power 1 over n. This actually is the same thing as a limit n goes to infinity of 1 divided by n squared to the power 1 over n, which I can rewrite in a slightly different way. So that's a limit n approaches infinity 1 over n to the power 2 over n, right? Which I can write also as, so this is not implication but equality, I can write it also as a limit n goes to infinity 1 over n to the power 1 over n by exchanging powers squared, and then just like in the first example, this limit is equal to 1. And so therefore lim sup n goes to infinity. If the limit is 1, then lim sup must be 1. So 1 over n squared to the power 1 over n. That is 1. So alpha is equal to 1 again. However, this series so this series here, sum n from 1 to infinity. In fact, I should also write the series as a series from 1 to infinity, because I cannot start from 0. 1 over 0 is not defined. On the so a series of 1 over n squared, this converges, as we will demonstrate in the next lecture or following lecture. And so we gave an example of two series. One series converges, another series diverges. Both of those have lim sup equal to 1. So that means that in this case, the root test is going to be inconclusive. All right, and then we'll start the next installment of this lecture by looking at the ratio test, and then we're going to discuss a few examples.